carbon materials for health, stealth, and energy. So before going to discuss this chapter, so what is the stealth? Stealth is nothing but low observability. Stealth technology means invisibility. The people will try to detect the objects, but our technology will make it as a low observable object or stealth object. This is what a stealth technology. Mostly this stealth technology people will use in defense sector. So what is the necessity of stealth technology? In defense sector, by using this stealth technology, invisibly we can attack on enemy. That is what the advantage of this stealth technology. In this stealth technology, how these carbon materials will play an important role. It is how we can make these carbon materials. Three types of carbon materials, mostly zero dimensional, one dimensional, and two-dimensional carbon materials we will use in this unit, or we are going to discuss those three materials. And again, if you define low observability or the stealth technology, it depends on the vehicle shape and avoiding the right angles to the metal plates. That is if you maintain particular angle, we can avoid the observability. And even chemical composition will play a major role. And even if we are using radar absorbing material, that is carbon material, in stealth technology will be, even we can mix these carbon materials in paints and we can go for the stealth application. These are the important applications of stealth technology. So if you come to the today's topic, that is introduction to carbon materials and fullerenes, production, properties, and applications, we are going to discuss. We know well already the periodic table. What it will tell us is the physicochemical properties of elements will be depending on the electronic configuration of element. If you see the fourth group here, after boron, carbon, silicon, germanium, tin, lead, this fourth group has an unique properties in the periodic table. Carbon, silicon, they could able to form catenation compounds, that is covalent compounds. Due to that, these carbons and silicon materials will play a major role in our daily life. In electronic industry, silicon, even OLED, organic light emitting diodes, or organic solar cells, carbon will play a major role. And our body contains carbon, protein, DNA, plants, everything is which is present in living thing is having carbon element. And if we come to the silicon, silicon is second most abundant element in the earth crust after oxygen. Due to that, the availability of these two materials, we are having a great impact on our daily life. If we come to the allotropes of carbon, we can classify the allotropes of carbon into two types. One is amorphous, the second one is crystalline. Again, the crystalline carbon allotropes we can categorize into three types: diamond, graphite, and fullerene. See that diamond is an insulator, graphite is an semiconductor, fullerene is a conductor. See, these materials are made up of with the same element, but they are showing different electrical properties. Diamond is an insulator, graphite is a semiconductor, and fullerene is a conductor. And if we come to the amorphous, that is a coal is the best example. And so we don't want to discuss about the coal and its significance, because our intention is to discuss about the nanomaterial, carbon nanomaterial. So even if you see the coal, we are the second largest producers in the world. This single slide will tell us the importance of the carbon materials. And one more important thing here is the carbon element has got 2 Nobel Prizes in 1996 and 2010. For Fullerenes, they have given a Nobel Prize. Fullerenes topic, a preparation of Fullerenes, and graphene. Even graphene also they have given Nobel Prize in 2010. And shortly people are expecting for one more, that is a carbon nanotubes. It may happen in future. This is the uniqueness of the carbon. The single slide will tell us the importance of the carbon allotropes. That is diamond, graphite, fullerene, and coal. And we are having other allotropes also. We have not mentioned in this slide. That is carbon nanotubes and carbon nanospheres. Other carbon allotropes are there, but we have not mentioned in the present slide. The comparison between these 3 major carbon allotropes, that is diamond, graphite, and graphene. This diamond is having sp3 hybridization, graphite is having sp2 hybridization, graphene is having sp2 hybridization. Graphite and graphene both are having planar structure, but the graphene is nothing but a monolayer of graphite. N number of graphene layers will give us the graphite. That is what the difference between graphite and graphene. Diamond is having sp3 hybridization, and it is very rigid since it is a tetrahedral, and carbon-carbon bond is very strong, and the covalent carbon or covalent bonding will give us the strength to the diamond, and diamond is one of the hardest material in the earth. And other physical and chemical properties of this diamond, graphite, and graphene, if you see, the band gap of diamond is 5.47. That's what it is. An insulator. Graphite is band gap 0.04 electron volts, and graphene is almost, it is a conductor. It is like a metallic thing. And CC bond length, even if you see, for diamond 1.54, and for graphite 1.42, for graphene 1.42. This is what the overall comparison of the 3 carbon allotropes. Carbon materials are there even in our ancient history. They have not coined the name nano during that time. They are using, it is not a new invention or any other new discovery, but people are using it, but they have not coined the name as a nanoscience or nanotechnology. This 326 BC, that is before Christ. A king called Purushottam has donated he was gifted a sword to Alexander. That sword is made up of with carbon nanofibers. This slide tells us the importance of the carbon fiber. Due to the carbon fibers, carbon nanofibers, the sword is having excellent metallic properties. That means we are improving the metallic properties, that is stainless steel or this uku properties, by adding in required amount of carbon nanofiber. Similarly, this Lyserger cup, which is made up of with an Roman people or Italian people. It was used in 4th century. You see, the same cup is showing 2 different colors. One is due to absorption and reflection, that is green color. So one more is due to transmission. The reason behind these 2 different properties, optical properties, is we are maintaining silver to gold ratio here in both the case, 7 to 3%, 70 to 30%, 70 silver and gold. We are maintaining 70 is to 30%. Due to that, what will be, it is having unique optical properties, which will be showing absorption and reflection properties as well as transmission properties. Due to this, this Lisarger cup is showing two different colors, same cup showing two different colors. And now the question is, why carbon nanomaterials? Why not other materials? We can use other materials also. The reason behind in this is the carbon silicon elements are most abundant elements, and it is easy for us even get a source material even if you want to synthesize in bulk quantity. It is easy for us. And three more scientific reasons why we are using these carbon nanomaterials. First one is electron confinement, and second one is surface to volume ratio. Third one is discrete energy levels. We already know the importance of electron and electron movement. Electron movement will decide the all other properties, physical and chemical properties of element. So now the electron is a powerful tool which is deciding these properties. If you control this movement, so we can create an novel nanomaterials, even either carbon or other metal oxide nanomaterials. Surface to volume ratio, we are increasing the surface area to volume. That is also one more important parameters. And discrete energy levels. Normal material will be not having any band gap. If you are making the bulk material to nanomaterial, what will happen? Those the mixed energy levels we are quantizing. That means discrete energy levels means we are having energy levels or quantized energy levels in nanomaterials. In bulk materials, we don't have. It's like a band, valency band and conduction band. This is a band theory we have already discussed. That means band theory will here help us to understand the properties of nanomaterial, carbon nanomaterials. Carbon nanomaterials. Now we will discuss these properties one by one. See that one same material is rice. We are making for different objects, that is idli, dosa, uttapam and rice. If you see within these four things, one will be very tasty. The reason is surface to volume ratio here. We are increasing the surface area, in which case we are increasing the surface area, and fourth case, that is in dosa case, what we are increasing the surface area. That's what it is. We feel it is a very tasty. The next is the uttapam. The next is idli. Next is boiled rice. You see that we are making the four items with the same material, but the taste is physical property. The taste is different. The reason is we are increasing the surface area. We are increasing the surface area of the material. That's what we could be able to see the different tastes. The surface area of the rice and the surface area of the either floor, rice floor. It is an rice floor surface area is in those case 260 meters square per kg. See that 1 kg of the rice floor is occupying 260 meters square. That is the area of a rice floor which can occupy the by the floor. Okay, rice floor. This surface area, if you are increasing, what happens? The active sites present on the rice floor will be high. If active sites are high, what will happen? Those active sites will interact with our tongue active sites, and we feel it is a tasty. This is what the scientific reason. And Still our rural Indians will use coal as a uh, teeth teeth cleaning substance, because coal is having, it is an activated material and it is having high surface area. Due to that, what will happen, it will remove the bacterial impurities as well as the any bacteria and color, this, anything which is present on the teeth surface will be removed by the coal, that is activated coal. And this is the importance of the surface area. That's what our carbon nanomaterials are having, an high surface area. Due to that, they are having unique properties. Similarly, one more material, that is sorghum. Just you see that sorghum millets is the per kg of sorghum flour is occupying 200 meters square per gram. Uh, Due to that, what will happen, even the people may be known these rotis, they are very tasty. Even if you compare, if it is a boiled item and fried item, we are activating twice. We are increasing the surface area by making it flour, and again we are activating uh, on it on hot plate. Due to that, what will happen, this will be very tasty. And the sorghum millets per kg, they will be having 200 meters square. But if you come to uh, the sorghum flour, see the 35,000 meters square per gram is it is an huge difference between this millet and millet surface area, millet floor area. And even then taking food with an hand is a challenging thing. For our Indians, it is not a challenging thing, since we are practicing it from our childhood. It is, instead of taking food with spoon and forks, if you are taking it with hand, we feel it is a very tasty, because we are activating it in our hand. And due to that, what will happen, surface area of the food will be increased. Due to the increase in surface area, what will happen, we feel it is a very tasty. But if you use the spoon, there's whatever the activation, there's an artificial activation is there, it will be there. But with our hand, we are if you compare, this is when compared to the hand needed material and the spoon feeding material, this there will be a lot of difference with respect to taste. And that's what mostly people will prefer to take food by hand. And the reason behind in these things is dimension versus activation. Is if you are increasing the activation, what will happen, is don't take it as an direct relation, just we are comparing a dimension. What will happen if you are activating it, if you are activating, dimension will be, that means with respect to size, it will be decreasing. Increasing the activation, dimension will be, that means surface area will be increasing. Okay, this is the reason, the scientific reason. And even boiled, fried, raw items, if you compare, you see that boiled is also, boiling is also one of the activation method, frying also one of the activation method, and raw. If you compare these three methods, activation methods, this raw, we no need to activate it. This is the fried item will be having more tasty, because due to the activation. This is the one of the, in all the cases we are reducing the dimension of the cabbage. You see that in more or less in all the cases it is the same, but still the surface area or the active energy which you are supplying in the form of boiling and frying, it will be different. That's what the fried items will be very tasty. Even in the case of potato, the fried items will be very tasty. And this is what the importance of the surface chemistry or surface science of the nanomaterials. If you reduce the size, we will increase the particle, we will reduce the particle size, and we will increase the surface area, and the physical and chemical properties will be different for these nanomaterials. And this slide will tell us the size of the computer from room size to hand size, how it can be due to the carbon and silicon nanomaterials usage in electronics or the silicon usage in transistor. Since we could able to reduce the transistor size, we could able to reach the computer in hand size. We can make the computer in hand size. That means from room size to hand size. You see the importance of silicon now. The silicon will play a major role. So now, if you want to go for transparent or flexible electronics, now we are shifting towards the carbon materials. Similarly, the evaluation of telephone. So without these two materials, it is not possible to innovate the shape of the telephone. And even in automobile industry, see the from invention of the wheel to development of the nano vehicle. It is without the usage of these nanomaterials, it is not possible. This is what the importance of the carbon nanomaterials in science and technology. Even you see this a player name called Pistorius from South Africa won a World Cup, which he was used the carbon fiber made, nanocarbon fiber made artificial legs. This shows the importance of the carbon materials. And so now we want to discuss about the dimension and how this electron confinement will vary with by varying the dimension of the material. Let us see the zero dimension. This is what is meant by zero dimension in nanomaterials. Let us, you take one room, X, Y, Z, let us take one corner. If you are keeping electron in the one room corner, what will happen? The electron can go through X, Y or Y, Z or ZX, or in between the space also it can go. That means we cannot control the electron movement in our room or in bulk material. That means electron can go anywhere. Let us, if you are reducing any one side of the room, that is height of the room if you are bringing to nano, or length of the room if you are bringing to nano, or width of the room you are bringing to nano, what will happen? The electron cannot jump. Let us see first in, this is a zero dimensional. Let us, we are bringing in the zero dimensional material all the dimension in nano size. That means we are making our room into a nano room. So now what we can control the movement of electron. That is electron confinement. Okay, electron we are artificially we are controlling the movement of the electron. That is electron confinement will be controlled by reducing its dimension. And if we come to the example for zero dimensional, zinc oxide nanoparticles or carbon nanospheres or fullerenes, all these three materials will come under this zero dimensional nanomaterial. And if we come to the one dimensional nanomaterial, that is carbon nanotubes. So we are having single wall and multi-wall carbon nanotubes as an example for this one dimensional nanomaterial, or even zinc oxide material, nanomaterial. You see this is a one dimension. In this case, there's a one, it is in micron size. You see that from this to this, it is in micron, but this to this, it is a nano, and Z dimension also in nano. You see that in every two dimension, it is in nano, one dimension, it is in micron. That means electron, we are confining to two dimension. That means we are controlling the electron movement in two directions. We are unable to control the electron movement in one direction. That means electron will travel only in the lengthy direction, that is in this direction. Electron will go in this direction now because of the shape, because of the dimension. Electron cannot come out from this particle boundary. Okay, electron cannot come out from this boundary. That means we are controlling the electron movement. And this is what one-dimensional nanomaterial. Even carbon nanotubes will be in the same shape. And these are the one of the important property. This is that is electron confinement. We are controlling in one-dimensional nanomaterial. And if we come to the two-dimensional nanomaterial, let us, this scale is in microns, don't worry. Just you see that in X direction, it is in micron, okay? In Y direction, it is in microns. But in Z direction, you see that this is the Z direction. This is like a thin film, or let us assume graphene. So now if you are keeping electron at this point, what will happen? Electron can travel in this direction, electron can travel in this direction, but electron cannot jump, or electron cannot travel in this Z direction, because the Z direction is in nano size. Let us assume this is in nano size. That means we are controlling the electron movement in only in one dimension. That is in two-dimensional nanomaterial, we could able to control the movement of electron in one dimension. This is one of the most important property, electron confinement. If you understand the electron confinement of any one nanomaterial, we can understand the entire nanoscience and nano technology. So zero dimension, what will happen? One minute, just we will clear this. Yes, in zero dimension, see that in zero dimension what will happen here, this is the electron. Let us assume this is three-dimensional X, Y and Z. In each axis, now the size is in nano. That means electron can go, it is in nano size. Electron can go in this direction, it is in nano. Electron can, that means all three dimensions, it is in nano size. Now electron cannot come out from this boundary. That is what how we are controlling the electron movement in zero-dimensional material. Similarly, in one-dimensional material and three-dimensional nanomaterial. If you understand this electron confinement and surface area concept, it is easy for us to understand the nanomaterials or carbon nanomaterials. Even one more three-dimensional nanomaterial in three dimension, that is in X, Y, Z. In every axis, it is in nano bulk size. That means it is a three-dimensional nanomaterial. Now in this material, the nano dimension is not there. Generally, the nanomaterials means particle size should be less than 100 nanometers. If you are studying that, the particle behavior, that is called a nanoscience and nanotechnology. But in this case, three-dimensional nanomaterial, above 100 nanometers, it will be in all the three axes. And even silica particles, see that this is more than 1 micron. Every sphere is more than 1 micron. That means it is a three-dimensional nanomaterial. Even we can call it as a nanomaterial because there is no standard definition for nanomaterial. Even 200 nanometers, we can represent even micron also in nanometers. So mostly less than 100 nanometers means we will be considering it as a nanomaterial. Even nanoparticles, metal oxide and mixed metal oxide nanoparticles will be, and how we are synthesizing the nanomaterials by two methods, top down and bottom up approach. This is, we are breaking the material into nano size, or we are taking atoms and we are making molecules and bunch of molecules will give us the clusters, and bunch of clusters will give us the nanomaterials. That means we can make this, or we can synthesize these nanomaterials or carbon nanomaterials in two ways: by top-down approach or by bottom-up approach. These are the synthetic methods, these are general synthetic methods which we are using for nanomaterials synthesis. Hydrothermal method, we are controlling the pressure and temperature in closed chamber, and wet chemical method, chemical reduction and oxidation method we are using. Physically, we are vaporizing the material and we are coating on target material, and chemically also we are depositing the materials, even sol gel method. These are the 5 important methods to synthesize the nanomaterials, and how we could able to tune the properties of nanomaterials, that is electrical property, thermal property, optical, magnetic and mechanic, by controlling the electron movement in this V valency band and conduction band, that gap, how we could able to control by adding impurity. That means by doping it, we can make. These are the chemical properties which the nanomaterials will be showing, an unique chemical properties, unique thermal properties, electrical properties, optical and magnetic properties. Due to that, what we can develop catalysts, we can develop thermal insulators or thermal conductors, or we can develop electrical conductors or electrical insulators, even optical sensors. We can even the magnetic material, that is we can make hard magnets and soft magnets. These are the characterization tools which we are using to characterize the nanomaterials. XRD, in order to know the crystallinity, particle size and surface area, and zeta potential, FTIR, thermal analysis and elemental analysis, and NMR. You see that mostly these are the materials which these are the equipments which we are using it for characterization of nanomaterials. We know already that we cannot see the electron, but we can see the nanomaterials. With these instrumental techniques, we can see the nanomaterials. You see each technique and what information we can get. Particle size, we can get the size of the particle, stability of the particle, zeta potential, a crystallinity size, XRD, elemental composition, elemental analysis, morphology, whether it is nano or bulk, by FSM we can, and surface area. By seeing the surface area value, just we can predict whether it is an activated material or not, and thermal property and magnetic property. The classification of nanomaterials, based on the dimension, we are classifying the nanomaterials, carbon nanomaterials, into 3 types. One is 0, 1-dimensional, 2-dimensional and 3-dimensional nanomaterial. For 0-dimensional nanomaterials, fullerene is the example, and 1-dimensional nanomaterial, carbon nanotubes is the example, and 2-dimensional nanomaterial, graphene or thin films, and 3-dimensional nanomaterials, carbon microtubes. In this lecture, we will discuss only 0-dimensional nanomaterial, that is fullerenes. This is the fullerenes and background to the fullerenes, and preparation of fullerenes and properties of fullerenes and applications of fullerenes. Based on the dimension, so we are the 0-dimension, 1-dimensional carbon nanotubes. You see that means electron can, we could able to control the electron movement. Electron cannot come out from this, or electron cannot come out from this Z or Y direction. Electron will be moving only in this direction. That means we are controlling the physical property of our carbon nanotube. That means electron can only move in this direction. It cannot move either in this or in this. This is what the advantage. This is what the electron confinement. We could able to control the electron movement in the 1-dimensional nanomaterial, and we could able to control the electron movement in 0-dimensional as well as 2-dimensional. Due to this, these carbon materials will show a different all physical and chemical properties. two-dimensional and one introduction to the carbon material, that is fullerenes production. And if we come to the definition of fullerenes, this is what is a fullerene first. Fullerene is a case of carbon atoms. Okay, simply we can define. And why this fullerene name was coined, this is how it was. This is an American architect who was an invented the, this is Buckminster Fuller, that is an called design. Just you see this is the Buckminster, and the person who is the same dome or the same the structure our fullerene will be having. That's what we are calling it as Buckminster fullerenes. Okay, this is the reason why we are calling them as in Buckminster fullerenes, because our fullerenes are having this dome design, that is pentagons and hexagons, and in the same fashion is our fullerene molecule is there. That's what we have coined the name called Buckminster fullerene. This is simply how we can define the fullerene. It is a case of 60 or 60 or more than 60 carbon atoms. Simply fullerene is a in 1996 Nobel Prize was awarded to these three people who, that is Kroto and Kull. These two people have synthesized the fullerenes. And types of fullerenes is we are having different types of fullerenes, that is C60, C70, C84, C20. See that C60 is an football, C70 is an soccer ball. You see that what is the difference between 60 and 70? 70 is in the form of soccer ball and C60 is in the form of football. This is having hexagons as well as pentagons. And the representation of C60 is, so we have represented the C60 molecule in different manners. That is, the C60 molecule has 32 faces, 12 or pentagons and 20 hexagons. If you come to the 70, 25 hexagons it has, 12 pentagons it has. The synthesis of fullerenes by KH experiment, that is Krasmer-Hoffman experiment. In this experiment, we have to take two electrodes which are made up of with graphite, and they will be in micron size. They will be having micron size diameter. One graphite electrode will be acting like anode, and one graphite electrode will be acting like a cathode. These two electrodes, we are keeping it in a chamber, which is an anode chamber, which is filled with helium gas. And if you supply the DC power to this chamber, what will happen is in between these two electrodes, we are supplying the, if you supply the power or electricity, what happens at anode, oxidation will take place. This graphite will emit the carbon atoms, and those carbon atoms will precipitate on cathode in the form of fullerenes. That is, the fullerene will be deposited on cathode electrode. The voltage which we are applying in this experiment is 20 to 25 volts, and the current is in 50 to 120 amperes. These are the experimental conditions which we are using for using to get fullerenes. And second thing is, once these fullerenes are formed on cathode, how will you extract them? Based on the fullerenes solubility, so we are getting the fullerenes. Let us assume these fullerenes C60, C70, C84, all different fullerenes are formed on the electrode. How will you separate them? By using the chromatography technique and by solubility technique. Just we are separating these fullerenes. solubility. Based on the solubility and this chromatography, just we are separating the C60 and C70. And by using even a U visible spectroscopy, we can. And the cost of the fullerenes, you see 1 gram of C60 is 16,000 rupees, around 1 gram of C70, 1.2 lakhs. 1 gram of endohydral fullerenes is 45 lakhs. You see that this is one of the rich material on the Earth's globe. This, we are having antimatter, but for the antimatter, if you want to buy antimatter, there is no supplier. And for fullerenes, people are there, even commercial suppliers are there. Even if you are interested, we can offer this amount and we can get. You see, this cost itself will tell us the importance of the fullerene. Endohydral and exohydral. The metal ion is there, metal ion is inside the case, metal ion is outside the case. We are naming it as an endohydral and exohydral fullerenes. First commercialization of these fullerenes was done by FSC, which was started by this Donald Hoffman. It's in 1990. This later this MC company, they have started commercializing these fullerenes in 2007. This is the synthesis and extraction of fullerenes. So now, if you come to the properties of fullerenes, the 4 important properties of these fullerenes. One is electron acceptor. Fullerenes are best electron acceptor. That means this fullerene is acting like an electron deficient alkene, and since it has an hexagons and pentagons, it has an carbon-carbon double bonds. That means, since due to the presence of this unsaturation or double bond, it requires electrons. That's what this fullerene will be acting like best or good electron acceptor. Even we are using this electron acceptor or fullerene in our the preparation or fabrication of organic solar cells. And fullerenes will be acting like a superconductors due to the crystallinity, and they will be used as in metal trapping molecules. Metals can be trapped with fullerenes. And the solubility of fullerenes, mostly these fullerenes are soluble in organic solvents. Fullerenes are not soluble in water. And it's because it is made up of with all carbon atoms. Definitely it will be soluble in only organic solvents, not in water. These are the 4 important properties of fullerenes. And based on the properties of fullerenes, the applications of fullerenes were classified into these different types. First, you see that fullerenes will be acting like a drug delivery vehicles. So, though they are having carbon atoms throughout the moiety, so we can functionalize with them. We can functionalize the fullerenes with different functional groups, and we can make it as an hydrophilic. We can improve its hydrophilic properties, and we can use them as a drug delivery vehicle or drug delivery agents. And fullerenes will be acting like free radical scavengers or antioxidants. Due to the electron accepting nature of fullerenes, fullerenes will accept the electrons from free radicals. That means anything which is going to stop the free radical generation, it will be called as antioxidant. That means fullerenes are the best antioxidant materials. So, where we require antioxidants. If you want to improve the thermal stability of polymers, polymers will degrade due to the free radical mechanism, or they will follow the initiation, propagation, and termination. During this degradation, in initiation stage itself or in propagation stage itself, these fullerenes will stop the degradation of polymers. That means they are the good antioxidants. And even we are using fullerenes as an electron acceptors. We know well we are using them in organic solar cell fabrication. And If you want to protect eyes or skin from UV rays or NIR rays, so we are using fullerenes. And if you want to irradiate the singlet oxygen, the fullerenes are the best thing. And fullerenes are an anti-cancer agents, and they will stop the cancer cell growth. And the fullerenes can improve the lifetime of human. Even we can improve the uh, lifetime of the humans. Let us see the examples, even this may be in coming slides. And fullerenes are used in neurodegenerative diseases treatment. Okay, neuron related diseases, if you want to control, we are going for fullerenes. And cardioprotector, even if you want to protect heart, so we are using fullerenes. And fullerenes are the best apoptosis inhibitors. That is, it will stop the cell division. That is what apoptosis. And MRI contrasting agents, and we can use even as a dry lubricant. Fullerenes can be used as a dry lubricant. These are the important applications of fullerenes. So one by one we see how we can improve the lifetime of human. You see here, this is a rat. The lifetime was given in x-axis and survival percentage. If you increase the month or lifetime, the survival percentage, if you are seeing water treated rat will be having the survival, you see that is an olive oil will improve the lifetime. And C60 olive oil, that is black color, you see that 66 months, 38 months to 66 months, even at 0%, at 100%, 90%, 80%, you see the lifetime. We, with this, the same formula can be applied on humans, and even we can improve the lifetime of humans. And this, in some countries already, this they are taking this carbon C60 and olive oil as an like a tonic, and they are improving their skin glow. And even they are they will be avoiding certain skin diseases. And fullerenes for health, you see that this, as we have discussed earlier, fullerenes will be acting like an drug delivery vehicles. This we can, because of this hydrophobic thing, they can enter into the cell walls and they can deliver the drug. And apoptotic or apoptosis process can be stopped by these fullerenes. And fullerenes will form a protective layer on DNA, and it will improve the it will stop the DNA damage. And the applications of fullerenes and other nanomaterials, the applications of fullerenes in medicine, all these things we have already discussed. Fullerene derivatives are fullerenes, which we are using in HIV treatment, because these fullerenes will stop the replication, HIV replication. It will stop the HIV replication, which we required in HIV treatment. And fullerenes are good electron acceptors. That's what we are using fullerenes in organic solar cells or organic photovoltaics preparation. Thank you for your patience.